Record. Okay, we're recording. Yes, we are recording. Are we? Yes, we are. Okay, this is the second last week of this whole course. Um, and we're going to start one last topic here, which is going to be what? Fiber optics. Okay, this is one thing we haven't talked about. And this is part of the which part of the telecommunications model that we studied. It will be the link. Okay. Now, fiber optics, it's basically field on its own. You can spend your whole life doing just that and make pretty good living. Just linking the fiber optics, setting up. This is the latest, hottest thing for some years now, and there's still a lot to be done. So if you decide to go into fiber optics in your career, you would be safe as far as getting employed. Okay. And making some decent money while doing this. All right, let's see how many people we have. We have 11 people. Oh wow, it must be heavy loaded with all the tests and all that stuff right now. As far as the tests and quizzes, we just have one more test, and I'm going to deploy this thing sometime later on this week, and that's going to be it. Same idea, online, just like the other quizzes and tests that we have done so far. All right. Let's not wait any longer. Wonder if we can cover this thing in this lesson, or maybe we're going to take part of next week's lesson as well for the fiber optics. Let's see how it goes. All right. So here it is. Cue it up, and there we go. Well, here is the. Here's something that everybody has seen at least once. It is the effect of rainbow. All right. Well, what's a rainbow? Rainbow is a split light. We have white light transmitted by the sun. This is the whitest white for us to ever get because it's the full spectrum for us in our existence, in this dimension, in this existence. White light is our sunlight. Okay. Now, when it passes through rain drops or water particles, the light splits, and depending on what angle you're looking at it, you can actually see the rainbow. Now, if it's there are some conditions for rainbow to occur. First of all, it has to be raining, or there has to be enough moisture in the air, and there has to be a visible sun. All right. So now, do you know where to look for the rainbow when you see those two conditions? When it's raining and it's sunny at the same time. Do you know where to look for the rainbow? Well, look for the sun and turn around. It's going to be behind you. Okay. That's now we're going to as we go along, you're going to kind of understand on what makes the rainbow. However, looking at rainbows is not the point of this class. However, this is part of the phenomenon that that actually has to do with the fiber optics and fiber optic transmissions. Okay, now. In this class, we're going to touch up on something that's called reflection, refraction, and refractive index, and something that's called the total internal reflection. Now, there's also a video link which I'm not going to play. Once you download this presentation, you'll be able to click on that, and you will most of the content would actually talk about the reflection, refraction, refractive index. So we're going to talk about reflection, refraction, refractive index. Get this thing from the video. I'm going to ask you some questions that have to do with that. But just as long as you understand the general idea of refractive index, I'm not going to put you through any calculations of calculating the index of things. All right, that's not the point of this course at this point. Of course, total internal reflection, that's a big one. You kind of have to remember that because all the transmission that is done through the fiber optic links actually depends on the total internal reflection. As much as we can get, the more of total internal reflection we get, the better for the optical fiber transmission. Okay, now just a quick thing. What is the difference between reflection and refraction? Okay, now let's say we have a we have something that's called an interface. Okay, can we see that? That would be the interface. This is the line that divides one medium from the other medium. So let's say this is air and this is water. Okay. Now, so this will be one medium, and this will be the other medium, and we're going to have a light traveling through both mediums. Okay, so let's say we start at the light traveling at the straight perpendicular kind of angle, perpendicular right to the water. Okay, it's going to the light is going to travel with the speed of light. Okay, and it's going to a certain speed, and then it's going to, as soon as it enters water, it's going to slow down, but it's still going to travel at the same speed. Okay, I'm sorry, at the same angle. So this is traveling. I forgot what's the speed of light here. Speed of light. Speed of light. Always. Now, speed of light would be 299,792,458 meters per square second. Here's the number. Okay, 299. 299,792 and 458. 458, okay, meters per second. That's the speed of light, okay? Now, if it enters water, water is going to slow it down, okay? And if it enters at a straight angle, it is just going to keep going at the straight angle, and it's just going to be slower, right? Now, when we change the angle slightly, let's say that angle here, normally it would go straight, but it's not going to go straight because the water is going to slow it down, and if it slows down, then you're going to have the light, it's going to refract, it's going to change the angle. Okay? So that's a refraction. It still penetrates the medium, but it changes the angle. Okay? Now, if you change the angle high enough, I mean, if you change the angle, well, if you increase the angle of the light hitting the interface, at some point, the light is going to not refract, but it's going to reflect from the water or from the interface. Okay. Air is in the top quadrant. You're talking Star Trek here? Okay. Anyway, so this is reflection. Okay, so this will be refraction. This will be reflection. And then there's a critical angle that is, if you just keep adjusting the angle, at some point, the light is going to travel right along the interface. That's called the critical angle. Okay, so so you know the difference now between the refraction. In refraction, it just keeps penetrating the interface, but it's traveling a little bit slower at a different angle. Reflection, it just basically bounces off. And this is what we're going to concentrate, because we need to reflect the light when we pass this through fiber optic link. Okay, now just so this is just a little tiny bit of a background of what we're dealing with here. Okay. All right. Now let's keep going with our presentation. Queue up, and just keep going. All right. So what do we see here? Over here we see a white light traveling through a prism. So this would be air here, and over here this would be glass. Right now, what's happening here? We see some of the red frequencies towards the orange, yellow, green, and then it would be in the blue light kind of a thing here. Now, why do we see the light split in this prism here? Any ideas? All right. The white light consists of all frequencies or all light frequencies. Now, light frequencies, there would be all visible light and invisible light. What do I mean by visible and invisible light to a human eye? Okay. A lot of the light we can see, but there's also a lot of the light that we can't see, but it's still considered as light as far as frequencies. All right. Now, the red frequencies, because it moves too fast for us to see. Because the light moves too fast for us to see, well, our human eye is sensitive to certain frequencies that we can actually detect. And some of the light frequencies we can detect with our human eyes, and some of the frequencies we cannot detect with our human eyes, although it's still some of the frequencies a little bit on the top of our vision or below our vision. They are also considered as light frequencies, instead of as opposed to like radio frequencies or sound frequencies, which we detect with our human ears. All right. Okay. Now, as you can see, the red frequencies are not being affected as much. Now, when we increase the frequencies towards the blue light, then those blue frequencies are being affected tiny bit more, increasingly more. So the red light is affected the least out of all these here. Then there's orange affected more, yellows, greens, and we go into the blue light. They are affected a little bit more. So they're being slowed down more. Okay, just keep that concept in mind here. Okay, maybe we're going to have time to analyze it a little bit further, but let's just keep going here. All right, now here is the representation of what's happening as far as frequencies. All right, so now when it happens to okay, so on the bottom here we have red frequencies, and the frequencies lengths, you can see that they are longer than the frequencies lengths of the violet. I'm just talking about the two extreme sides here, and then there is that everything in between here. All right, so it's the red light would be 620 to 750 nanometers of a wavelength, which is the one period of the frequency of the wave. Sorry. And then this translates into the frequencies. So the longer the wavelengths, the lower the frequencies, obviously. Okay, so the red light would be 620 to 750, which would be about 400 to 484 of terahertz in frequencies. Okay. Now, when we move towards the higher frequencies, you can see that the wavelengths are going to be shorter, and obviously the frequencies are going to be greater. All right, it's not a big philosophy here. All right, you can download this presentation and you can analyze this if you wish. All right, or maybe you should. All right, now, when it comes to the spectrum here, here is our visible light, right from this point here up to this point. Let's see if I just visible light. So somewhere around between 400 and 750 nanometers in length. Okay. Now below there would be ultraviolet light. Sorry, higher frequencies would be ultraviolet light, longer wavelengths, higher frequencies. So the light is going to go more blue, more blue, more blue into violet until the point that we actually can't see it anymore, but it's still considered a light. All right. Now, when we go towards the other end here, we see visible light, and then below the longer wavelengths and lower frequencies, that is going to be the infrared region, okay, which is infrared means below red. And this is basically where the fiber optic links operate. That's where the fiber optic transmission is happening, in the lower lower frequencies or longer wavelengths. All right, now I'm just going to go back a little bit here. The reasoning behind that, and we're going to come back to it towards the end of this presentation. You see red light, which is the longer frequencies, are affected less by the glass medium, simply because the longer wavelengths, they do not interact with the small glass particles as much as the violet light does. The red light is a longer frequencies, and they basically ignore the small particles, the small glass particles, or whatever is in that glass. Okay? The violet light, they are shorter frequencies, and they are closer to the size of the small particles of the glass. So let's say, I'm going to use kind of a funny analogy. Well, the violet light, they can relate to the smaller particles, and they're going to stop and talk for a while. So that's why they're going to slow down more. The longer frequencies, they're the big guys. They just ignore the smaller particles, and they just keep moving along. So they're affected less. Okay. So now, if you look at this, if you were to choose which wavelengths to choose from, in order to use those frequencies in the optical signal transmission, of course you would choose the frequencies that are affected less by the medium that you're shooting it through, as opposed to the ones that are affected more. So that's the reason why the red light is being chosen, or the infrared light is being chosen for fiber optic transmissions. They are affected less by the glass particles. Yeah? Okay. Now, fiber optic communications typical wavelengths would be, sorry, go back. Typically would be 780 nanometers, 850 nanometers, and 1310 and 1550. These would be the around those frequencies. This would be where the fiber optic transmission mostly happens. However, when the technology advances, some of those some of the choice might be abandoned when it comes to some that full spectrum, that's called full spectrum fiber optic cables. However, there is a reason why those frequencies are being chosen as carriers. You know what a carrier is? A carrier is a frequency that you tune the transmitter to that carrier frequency, and then in order to receive that carrier frequency, you tune the receiver to the same carrier frequency, and then once they both lock on to the same carrier frequency, they establish the same ground, sort of as the same kind of language that they speak. All right, and then once they both, the transmitter and receiver, are tuned to the same carrier frequency, then whatever the transmitter does to the carrier, the receiver is going to receive, and the modulation type, it can be translated into different things, like different type of signals or pulses. So when the transmitter modulates the carrier frequency in terms of sending pulses, then because the receiver is tuned to the same carrier frequency, is going to be able to see those pulses. Or maybe there is going to be a sound waves. The carrier is going to be modulated with the frequency of sound waves. Then you're going to receive the sound waves on the transmitter, on the receiver end. Okay. So these would be the typical carrier frequencies for the light transmission in fiber optic links. Okay, and the reasoning for that is called water bands. We're going to analyze that towards the end of this this presentation here. Okay, just keep that in mind. There are certain carrier frequencies that are chosen to be the best for fiber optic transmission. All right, fiber optics. Welcome to the world of fiber optics. All right, now, when it comes to distinguishing two basic fiber optic links, excuse me. Sorry. Okay, gotcha. All right, thank you very much. All right, I just turned the sound off for a second, and I guess I pressed the wrong button. Okay, let's go back here. All right, now we're distinguishing two basic fiber optic links. It would be single mode and a multi-mode. Right away, you can notice the difference between single mode and multi-mode is that the core, okay, is in the multi-mode is larger diameter than the single mode. All right. Now the cladding size, cladding is basically the surrounding material that surrounds the core. Now, the core and the cladding are both pure, quite a pure glass, except that the purities are a little bit of a different grading, okay, when it comes to core and the cladding, in order to create different index of refraction. And just to make the long story short, okay, the point of this whole exercise is that if we have fiber optic, here's a core, and here's the cladding. All right, and of course that's the fiber optic link. Okay, the point of this whole thing is to create a mirror inside the core. So when you shoot the light can travel through the core. But if you shoot the light at a slightly different angle, then this interface here is supposed to act like a mirror and reflect the light, so it just bounces off the walls and travels. Okay? Now, if you insert the light at too much of an angle, then of course you're going to get a refraction, which is something that we don't want. Okay? So this would be the angle of acceptance when it comes to dealing with fiber optic links. Okay, you can shoot the light with only at certain angles. Okay, now with the multi-mode, with the single mode would be, let's say, the line. This will be the mode. All right, so it will be single mode, and the only whoops, I'm running out of ink here. The only mode that travels through a single mode would be the one that goes in a straight line. That's why it's called single mode, or single line, single angle type of a thing. Okay? Now, in the multi-mode, you have a larger core, and the light enters at slightly different angles. So you're going to have a little bit of a bouncing effect happening here. Now, just because I drew like maybe 3 modes here doesn't mean that there's only 3 modes. Basically, it's a burst of light entering the core at different angles. So the light is going to be slightly more dispersed in the multi-mode than in the single mode. In the single mode, you get straight light going through because the core is so tiny. There is no room for the light to actually bounce as much. Ideally, the bouncing would be considered 0. It just would be a light traveling in a single at their single angle. That's why in a single mode we can transmit the light at the greater distances because the signal keeps its integrity over a longer distance than in the multi-mode. Of course, the single mode fiber optic lines are more expensive to produce, and the equipment that that is used to transmit and receive is also way more expensive than the multi-mode. Okay, so single mode more expensive, can travel longer distances. You're talking about 100 kilometers. Different sources are going to give you different. So if you Google the distance for the single mode, different sources are going to give you different lengths. Some of them are going to give you 50 kilometers. Between 50 and 100 kilometers, you're going to have the different opinions or different sort of opinions, different information on how far the light can travel in a single mode. Okay, that depends on when this document was released and by whom and what equipment is being used, right? Now, so let's say the single mode can transmit light in, let's say, around 100 kilometers. The multi-mode, the signal doesn't keep as much integrity as in the single mode, and the light can travel maybe 2 kilometers, 3 kilometers. Again, different sources are going to give you different different information. In the single mode, usually single mode fiber lines are used for long distance transmissions, so that would be between cities or within the cities. Within the city, it will be like more like outdoor type of linkage. Okay. Now, when it comes to multi-mode, most of the time you're going to see the applications as far as LAN, local area network environment. So with single mode, you would connect stations within the city or between cities. With the multi-mode, you can mostly you're going to see links between the communications closets. So there will be one horizontal RAN area that the closet is servicing maybe 50, 60 computers, and they all come to one communication closet. And there'll be another communication closet that services another 20, 30, 40, 60 computers. And then these 2 closets could be connected by one fiber optic link, which will be multi-mode. All right, it's all going to make sense as we go along. Okay. I think we're going to take 2 lessons when it comes to dealing with that. I have 2 presentations. One is basically the principles involved, and the other one would be practical applications. I think we should split them into two different lessons here. All right, keep going here. All right, so as you can see here, the light enters the multimode at different angles with the multimode, and the light enters only on the one angle. So now, of course, over here, we would employ something like a laser to insert the signal, and over here would be LED. And this part of the fiber optic link is called a core, and the part that surrounds that is called a cladding. Now, when you watch the video, this one here, where is it? Yeah, this one here. Oh, there we go. When you watch this video, you're going to see, you're going to get the concept of refractive index and total internal reflection. Okay? Now, the efficiency of the transmission or the fiber optic transmission depends on the total internal reflection. We want the light to be all the light that we inject into the fiber optic link. We want this thing to be contained within the fiber optic link. So basically it happens to the total internal reflection. Refraction in fiber optics is something that is bad. It's basically a leakage. Now, where would the refraction would happen? Let me just. Okay, so let's say we have a straight link. Okay. And we inject the light. The light bounces at certain angles that are not making the light refract, they're making the light reflect. So the fiber optic transmission depends on the total internal reflection of the light. And reflection, that basically the light stays within, reflects, bounces off the walls, and it's kept within. Now, it also depends on the angle. Remember when I told you about if you inject the light at the too much of an angle, then the light is not going to slide along the wall. It's going to basically have enough energy to puncture through the interface. So when you have a can I get the all right? This is going to be easier to see. Okay, we have a, let's say this is a fiber optic link, okay, straight one. The light travels through that, total internal reflection, no problem. When you start bending the link, inside the angles inside the fiber optic link are going to be affected. And if you bend the fiber optic too much, you're going to actually see the light escaping. The fiber optic link. So you're going to have signal losses because of the angle that the light hits the interface between the core and the cladding. The angles are going to be too much, and the light is going to start. The more you bend, the more losses you're going to get with the fiber optic link. So there's only a certain amount of band radius that you can then you can put the fiber optic link through. Okay, generally speaking, you want this thing to be as straight as possible. Right. All right, keep going here. All right, so with the multi-mode, the core would be around 16 microns. 60 microns would be 60 micrometers. Okay. Now, when it comes to multi-mode, single mode, you can see that the core is basically 10 times, oops. There you go. The multi-mode, the size of the core would be about 60 microns. And the single mode would be 10 times less, around 5.8 microns. That would be the size of the core, okay, in a single mode. Right? Now, you can see them side by side. Now, you can see the size of the cladding. Here. Cladding is the material, which is the glass of different type of consistency. It's also a pure glass. The cladding is about, what do we see here? 125 microns in both cases. So the cladding is the same. Yeah. And the cladding is the same here. So this is a single mode, this is a multi-mode. How can you tell the difference? Well, single mode is going to have much smaller diameter of a core. Okay. And whatever else is here is the coating. So when we strip the fiber optic, we're going to strip the coating of that. Okay. Now, the cladding, again, the same. And you're going to have some of those questions on the test, the size of the, I'm going to ask you about the size. And I'm telling you, the size of the cladding is the same for single mode and multi-mode, 125 microns. Now, typically it would be around 60 microns. It would be the size of the core for multi-mode, and typically 10 times less, maybe 6 to 10. Again, different sources are going to give you different information, but around 10 times less than 60. So around between, this one says 8 to 10. Well, it could be 6 to 10 microns of a single mode. And then 250 microns and 250 microns. So when you strip the fiber optic right to the cladding, right, you have a same idea of a stripper as the copper, but it's made for the fiber optics, different type of instrumentation. But you go through the same motions. You just lock the stripper grooves onto the fiber optic and strip that right into the cladding. Okay? If you strip single mode and multi-mode, and you look at them just with your bare eye, you won't see the difference. You're going to have to look at the microscope, through the microscope, to see actually what's happening inside. You can see the core. This is as far as the sizes of fiber optic links. Now, typical anatomy of the fiber optic. Let's say here's a core. It's about 8 microns. Here's the cladding. Okay, again, 125 microns. Then there's a coating or a buff coating, and the buffer and the jacket. Okay, so this one shows core, cladding, buffer, and a jacket. Now, the bread and butter of fiber optics is basically the core and the cladding. All the fiber optics contain that, the core and the cladding. Now, what comes after that, that depends on the purpose of the fiber optic link and the environment that this fiber optic link is going to be subjected to. So some of them, some of the fiber optics you're going to see nice and flexible. These are meant to be used on the inside when you're connecting the fiber optic links through between the closets of the LAN communication closets. Now, when you run those fiber optics outside, you are going to see much harder kind of protective layers on that. By the way, when you see something like this, when you see something like this on the road, let's say there will be utility poles here. There's a utility pole, and there's another utility pole somewhere, and then you're going to see lines like this, thick black line, okay? And you're going to see something like black, kind of a barrel-looking like. You see it all over the time, all over the place. Device. It's just like a barrel tubing type of a device, and you're going to see something like this around that. All right, and you're going to see lines and lines here. Well, what this is something that's called a FOSC. Okay. I'm running out of ink. Okay. Fiber optic splice closure. Very popular thing right now. What's happening here? These black heavy cables, these are the fiber optic lines that are running into the FOSC. Now, and quite often you're going to see a van. Let's see if I have my drawing skills here. There's a van, wheels, okay? And you're going to see sometimes a ladder somewhere here, okay? And then you're going to see that taken off and being put right inside that van. Well, the FOSC, fiber optic splice closure, is that inside there will be a technician opening the FOSC, working on it, doing splices, usually fusion splices, and we're going to talk about that later on, maybe next time we see each other. That person is doing the splicing, and then they're going to close that, protect it from the elements, and hang it back onto this thing here. So these will be the single mode fiber optic lines on the outside. Okay, so now you know what those are. Okay. Yeah, we're going to take 2 lessons for this thing here, because the practical applications, I'm going to spend a little bit time. I can't rush through this. All right. Cleaving, you're going to see the video link. Safety, you're going to see the video link, and that's pretty much it for today's class. Now, when you download the presentation, please watch all these suggested YouTube links. I'm going to ask you some questions on that topic here. Now, just as a review for today, can anybody tell me what would be the phenomenon that the fiber optic transmission depends on while going through the fiber optic links? What would be the phenomenon that we use? What makes it possible for the fiber optic signal, for the light signal to travel through the fiber optic links? Something that goes with the total. Anybody? Or is everybody sleeping or watching movies when I'm presenting? Come on, guys. Nobody. Okay. Well, I'll leave that question for the next. I'm going to ask you the same question at the very beginning of the next class. Okay. Now, as far as the labs, we're all done with the labs. I am going to be today and maybe tomorrow and the next week in class, in case somebody is running behind with some of the labs, then you're going to have a chance to perform the labs that you're missing. All right. So there is no more new labs. If you have done all the labs, you're good. Don't need to show up for the class. But you're welcome to show up if you want to perform some labs that you have missed. Okay. I'll see you when I see you, and I'll talk to you when I talk to you. Stay healthy and safe, and I'll be back. All right.